Good morning, everybody. My name is Natalie Aguilera, just like Carla said. This is my research that I did over the summer using multi-sensor environmental data to investigate debris flow hazards. I would like to acknowledge my mentors at the USGS office, Liam Toney, Kate Alstad, and Elaine Collins. I would like to acknowledge the RECCS team, and that would be Alicia Christensen, Carlin Loomis, and Madison Payne. So I would like to show you a debris flow video from July 21st. It is sped up by 10. Keep in mind when you watch this video, look for the seismic surges. So like I said, I would like to show you a video of a debris flow, and keep an eye on the synced pulses. This video is sped up by 10. It's slower in real life, but still intense. Okay, so, oh no, not this again. So, what is a debris flow and why does it matter? Debris flow consists of rain, mud, and rocks, and goes down slope really rapidly. And it matters because it can denude slopes, bury floodplains, and devastate people and property. Why syncing sensor data matters? So in this project, I was looking at different types of data. I looked at rainfall, laser displacement, seismic and infrasound data. And with that enables real-time analysis and early warning systems. Understanding the start is the key to keeping people safe. How syncing data supports early detection. Data syncing sharpens detection precision, can support development of real-time hazard alerts, and improves ability to issue alerts with critical windows. So, over the summer, I was looking at one specific site in Colorado named Choffs Cliffs. It is steep, storm-prone, and populated area. It is by Salida, Colorado. This area is very susceptible to debris flows due to the sediment being very brittle, and this can cause debris flows. So at Choffs Cliffs, there is two sites that the USGS installed in mid-May. It's the lower site and the upper site. That would be the upper site, and that would be the lower site. So like I said, there would be different instruments at these sites. So there's infrasound instruments, seismic instruments, and weather instruments regarding rain. And an infrasound instrument is it detects low frequency at really low sounds. So how did I use this data and how did I filter it out? First, I used the scientific Campbell data. It was just in a file or like a DAT file. And then I used the IRIS FDSN to get seismic and infrasound data that was raw. And then I filter it using Python. I first used OzPy, that was for the seismic and infrasound data. It's a seismology tool that seismologists use as a Python package. And I also use different packages in Python, like pandas, to use data frames to go through scientific data. With this, I then, when I did the merger and then filtered, I used matplotlib to visualize and plot the weather, seismic, and laser data. And that's how I got my final plots. So, oh no. So we're going back to the video that was resulting on one specific day on July 21st, 2025. Like I said, keep an eye out on those surges. So on this, it's like a 15-minute time limit. This is a plot over time with distance. So there is a laser. So with this laser, it is pointed at the channel, and then it can sense the surges. So there is one surge right here at this time, and you can see also the seismic data. It is not time aligned because the instruments are spread out at different places. So you can see that they're not aligned at the same time. So that's why I put diagonal lines. And at the end, yep, peak rainfall at 0.6 millimeters per minute. That caused the debris flow. And after that, you can see, I also have a pointer. After that, you can see it causes the disturbance. Yep. Seismic surges after the peak rainfall. So this is also another map that I had. It's replacing the laser displacement. So that red line is the laser. And those three, the 4, 5, and 6 are the geophones that take the seismic data. Yep, so the seismic signals imply that ground motion intensified as the material moves down slope, supporting evidence of a debris flow. This timeline pattern of the spring spike, laser signal drop, and the seismic surges from the upper site reflects a short lag between the rain signal, laser displacement, and the seismic trigger, just like I said in the previous slide. So conclusions, rainfall, laser displacement, and seismic pulses were timed aligned during debris flow activity. Multi-sensor data gave strong evidence for a rapid slope response to rainfall. And these results show that seismic monitoring can contribute to hazard detection and mediation, especially in deep terrain. And that's a picture of me at their lower site digging a seismic node on the ground. And thank you for everything. And